Well, thanks for inviting me to talk on this subject. It was the slides I started making were for the American Nuclear Society and the Canadian Nuclear Society, and they were very popular. Since there's a lot of medical people here, I added a bunch of slides, deals with medical issues, health issues, but the main purpose was to assess, comment on the appropriate levels for evacuation from radiation disaster, release of radioactivity. That's my background. I studied engineering physics and nuclear sciences, and then I made radiation detectors, built with my own hands. And then I came to Canada, returned, and worked at Atomic Energy of Canada for over 25 years, mainly on designing CANDU reactors. And after I retired in 2000, I've been doing engineering services. I'm still working. I'm a member of a number of societies, professional societies. I try to keep up with the technology and to meet people and communicate. And I got into the learning about health effects of radiation after I heard a centennial talk by Dr. Myron Polyakov in San Francisco in 1995. It was 100 years after the discovery of X-rays. And he talked about how X-rays have been used in medicine for a century. And he mentioned also health effects, positive health effects, just from the radiation. And this blew my mind. I said, what? This is totally different than what I've been taught, learned all my career. So I started to look into this, and I challenged him, and finally I came around to taking a really important interest in this, because this affects nuclear energy, the future of it. It's already affected for many years, but it also affects medicine and a lot of industrial applications. Anyhow, the main point of the original talk was that the radiation in the Fukushima, the radiation levels, comparable to high natural background areas. And if you look at the United Nations Scientific Committee of Effects of Atomic Radiation, they put out a report every few years. This is a United Nations committee, and in 2000 they give a nice list of high background, natural background radiation areas. The second point is that in the 1920s, there were a lot of radiologists working, and they had a radiation protection standard that was quite good. And it was based on defining a safe tolerance level of, 680 millisieverts a year, but they were based on Rontgen in those days. The third point is that 1 millisievert of radiation-induced DNA damage is 6 million times lower than spontaneous DNA damage. People have always assumed that our DNA was stable and there was, we could rely on it not changing, but it turns out it changes at an enormous rate, and when you look at the radiation effect of normal background, it's 6 million times lower. So radiation effect on DNA damage is negligible. And yet everything you hear today about radiation is that it's affecting our DNA, it's causing genetic mutations, it's increasing the cancer incidence, cancer mortality. So the fourth point is evacuation caused much unnecessary suffering. There was no need to evacuate. So let's go on and talk about the earthquake. As you know, it was March the 11th. It was a magnitude 9 earthquake, and the remarkable thing is when I used to analyze and study earthquakes, they usually, the strong motion lasted 30 seconds. Well, this one lasted for 3.5 gut-wrenching minutes. 3 major energy releases, and then you see the aftershocks, 10 of them, and they're really quite severe. And this is where it happened, off Sendai. And there is the nuclear reactors that got the tidal wave. And so speaking of tidal wave, the tsunami within 45 minutes after the earthquake, the series of these waves hit the coast, and 4 prefectures along the Japan were affected, and the wave height was accentuated by the coastline, the shape of it, and there's also movement of the ground, significant, even lasting. And at the site, it was 14 meters high, the highest wave. Now, there's 4 basic requirements. 3, the ones I used to worry about, and then 4th, we got to know what's going on. But the first one is to control reactor power, and that's what they did. They did shut down the plant. The second one was to cool fuel. Now, we have cooling mechanisms in place, but it's also, when you shut the reactor off, it's still producing heat because of the radioactivity of the fuel, and it produces it forever. So there's always an ongoing problem to keep the fuel cool, to make sure that the radioactivity is contained, because if you don't cool the fuel, then the containment around it melts and the radioactivity comes out, and then it gets messy. Then the 4th requirement is to, when something bad happens, or even when it's operating normally, is to know what's going on. But especially afterwards, when people move away, evacuate, you still want to know what's happening in the plant. So here's the tsunami inundation. You can see this is the normal level here, and it was 14. The normal plant level is 10 meters, and this went up 14 meters above sea level. And you can see the main control room was dry. The battery room got flooded. The switch gear, all the controls were all soaked. The emergency diesel generator room was covered with water. So they couldn't cool the reactor after it was shut down. The important thing to mention is that the power lines were broken. They had power failure for several days. In fact, in Sendai, I was talking with Dr. Sakamoto, who comes from there. He said there were 3.5 days they had power failure, and people living in high-rise buildings were under a lot of stress, having to go up high stairways for many floors. This is what the pumps and pump motors look like, the cooling ones, when they're underwater. They don't work very well. And so within a day or so, the fuel began to melt because it wasn't being cooled. And the reactor unit number 1, most of the fuel melted down and came through the containment pressure vessel. The other 2 reactors that were melted, the units 2 and 3, there was a bit of release and partial melting of the fuel. So that was the result of the lack of cooling that wasn't maintained, the cooling that was not maintained. So the heating up of the fuel, it's covered with zirconium sheath around the fuel pellets. It's cooled with water, and the water, of course, turned to steam, and there was a reaction between the zirconium and the steam, produced a lot of hydrogen. So this is containment. This is a suppression pool to keep ongoing cooling if you had pumping. And there's a venting arrangement that's supposed to relieve pressure. And this didn't work too well, and so instead of the hydrogen going up the stack, what we had was it accumulating in the building, and the hydrogen exploding and blowing the building apart, the outside building. This is not really containment. This is the containment boundary here. But you can't maintain containment if you don't have cooling. You get overpressure and you have to relieve it. The used fuel is kept on a pool here. It's a used fuel pool, and this is outside, and this is fuel that was removed from a reactor some time ago. So when the hydrogen exploded, you can see this Unit 1 reactor building was blown away. It's like a factory structure. It's not a reinforced concrete building. This is also blew out, and the hydrogen got from this building to this building, so this one also exploded when this hydrogen exploded. So you had the pressure vessel, and the secondary containment was gone. And so what happened next was all the radioactivity got out. And so you can see different bars here, different colors for the radiation levels from the radioactivity that was released. And so these are radii. This is 20 kilometers, this is 30 kilometers, 60 kilometers, and the Americans decided that they had to evacuate at 80 kilometers to be really, really sure. Now, when you look at the red area, which is the high radioactivity area, well, that's the range in microsieverts per hour. And if you take the highest number, 91 microsieverts per hour, and you multiply by the number of hours in a year, this is the radiation average dose rate that a person would get if he sat in this high radiation area. You got to remember that number because this is, I'll get to it later. But if you, since we're living in New York, let's see, where's Manhattan here, and this is what, Long Island? That's New Jersey. So the area that was evacuated corresponds to that in Japan. That's the Fukushima plant. And this is what equivalent would be in the US, in New York. Gives you an idea. This came out of the New York Times. Now, getting back to radiation levels. The highest radiation level, the red area, the upper range, is comparable to high natural background radiations. In Iran, Ramsar, it's 260. There's areas in France and Brazil with 800 millisieverts per year. This is the average rate. This is a linear scale, so it's from 1 to 10 millisieverts a year. And Washington, D.C. and New York Grand Central Station, it's about 6 millisieverts a year. The global average is 2.4. If you look at this peculiar thing to do, but if you take the radioactivity that's released and you average it over populations, you get radiation exposures that are quite low. And so this is the natural range, and above here you get into medical diagnostics. And so the main point of this slide, which is based on unsecured data, is that there are areas naturally radioactive that are the same as the area, the red area in Fukushima, around there. Now, talking about natural radiation areas, this is Chernobyl. This is low contamination area, medium and high contamination area. And here are other countries in Spain with areas that go up to this sort of dose per 70 years. And here you can see in Finland, it's even higher than the high contamination area in Chernobyl. And nobody evacuated Finland, but these areas are still evacuated. So the conclusion you can draw here is natural radioactivity is fine, but if it's human-made, then it has to be evacuated. It has to be cleaned, it has to be scraped. So let's go back to the radiologists. From before 1920, didn't have any regulations. So radiologists were getting quite a dose. So they were treating one patient after another with x-rays, diagnostics, and then they discovered these people were getting cancer, higher mortality. So in 1920, they introduced protection regulations, and the level was first they came up with the idea of a tolerance dose, so much per day for entire life. The level was 0.2 Roentgen per day, and they had an interesting way of finding that number. They said, well, 600 Roentgen produces a burn or a erythema dose, average accepted. And so we're going to go to 1/100th of that, and we're going to spread it over 30 days. And so they came up with this limit, and they've been using it for many years, and it was found to be acceptable. No increase. The radiologists did not have higher cancer mortality with that limit in place. So, in fact, in 1924, they had a meeting of the American Roentgen Rage Society, and he said this tolerance dose rate is a dose rate that could be tolerated indefinitely, means day after day for the entire working life. And this level is equivalent to 600 millisieverts per year. Now, where did you see that number before? That's the level of these people living in 91 microsieverts per hour, the red area where the contamination came out from the reactors. So this is an acceptable level for radiologists to work every day for their entire life, or working life. So the British scientists, Smith and Dole, this Richard Dole, a very famous scientist, did a study of radiologists from 1897 to 1976. There's 300 studied prior to 1921, when there was no regulations on radiation exposure. The society did not have a dose limit. And there's 1,000 or so afterwards that were studied in this study. They found neoplasms are cancer mortality. They compared the radiologists with social class 1. They have a nice class structure in the UK. And so they found that 44% higher mortality. And I'm not going to get into discussion of p-values because I don't understand it, as was established earlier. But after 1921, when this 1920, when the standard was introduced, you can see that the average mortality for cancer went down. And this was also true for other causes. There was actually a lower mortality overall for other causes of death. So the conclusions of that study was after the radiation exposures were limited to less than the safe tolerance dose level, cancer mortality decreased. It decreased from 44% above social class 1 to 21% below social class 1. And mortality from other causes decreased. So back in the 1920s, they had a perfectly nice, good standard for protecting radiologists. It was actually beneficial. Then Ed Calabrese came along, published this paper, and he's called The Road to Linearity. He's trying to understand how we got from a safe tolerance level to the linear no threshold model assumption. He said there were 3 drivers for this change from the safe level. The first one was a theory of eugenics. It's a pseudoscience, and we've heard a lot about pseudosciences. He postulated there's a crisis in the gene pool, the human gene pool. People were worried way back then. It was very popular and very fashionable to believe in this theory of eugenics and to try and protect the human population gene pool from deterioration, human race. So we had all these geneticists very interested in preserving the human gene pool. Then Hermann Muller did some studies on radiation. He postulated that radiation would cause mutations, and so he studied fruit flies and he irradiated them with very high doses. And he published a paper saying, well, I discovered that radiation causes mutations in fruit flies. And then they started to talk about proportional to the dose, linear assumption. And I guess it made sense if that's all you were thinking about was damaging DNA molecules, that it should be proportional to radiation. And then we had, after the bombing of Hiroshima and Nagasaki, very renowned scientists all over the world, especially in the US, not only Muller, but Pauling and others, Nobel Prize winners, created a radiation scare to try and get the scientists to stop, well, the people's military to stop testing bombs and building more. Of course, Russia was doing it, and they thought that by producing this radiation scare, with the fallout having enormous consequences on cancer and damage to babies, that so they pushed very hard this radiation scare. So by 1955, a policy change was introduced in radiation protection due to Muller and others and political activities of scientists to reject the idea of the permissible dose. They came up with there's no safe radiation level. Radiation-induced DNA damage is linear with dose. It's cumulative. It keeps adding more exposure, more damage, and that all the mutations are harmful. They adopted a concept of cancer and genetic risk, kept it small compared to other risks in life. And this is one of their quotations: since no radiation level higher than natural background can be regarded as absolutely safe, the problem is to choose a practical level that, in the light of present knowledge, involves negligible risk. And they came up with this idea of as low as reasonably achievable. And then when implementing it, they dropped the word reasonable. Now, Lauriston Taylor, who was a founder and former president of the National Committee on Radiation Protection and Measurement, denounced the use of the linear model to calculate annual deaths, cancer deaths from X-ray diagnosis. These are deeply immoral uses of our scientific heritage. No one has been identifiably injured by radiation while working within the first numerical standards in 1934. So here you are, this founder of our radiation protection goes back and says the LNT is not valid. So now we have studies on genetics, this genes going on in the 1980s, and there's a publication in Radiation Research in 1990 by Daniel Billen. He does a commentary, and what he says is, geez, we've discovered that the DNA is not structurally stable, so we can't really preserve the human gene pool because it's pretty flaky already. It's not structurally stable as once thought. On the contrary, there seems to be a natural background of chemical and physical lesions introduced into cellular DNA by thermal as well as oxidative insult. So to stop that, you have to stop breathing, and you have to stay cold, because this is damaging the DNA, and it's quite a rate, a very high rate. And he goes on to do a comparison between the natural background of lesions, the spontaneous DNA damage rate. This is what they determined, all these scientists. He's doing a commentary on all the results that have been studied over 10 years before then, 1980s. And then he looks at the radiation rate, and he says for each centigrade, you get this many alterations per cell. And these are all alterations per cell per day, so that's quite a large number. Now, if you take that normal background order of magnitude, 1 milligray per year, and you compare it with the spontaneous rate that's occurring, and you put it on the same scale as cells per day, you find out that the background is 6 million times lower rate of DNA damage than what's happening naturally from oxygen breathing and reactive oxygen species and thermal effects. So radiation is not really a significant cause of cancer when you're looking at the sort of levels of background radiation. And we've known this for more than 20 years. So this is Myron Polyakov and Ludwig Feinendegen model based on calculations and measurements. They said that if we didn't have antioxidant production, there would be 10 to the 9th alterations per cell per day. That's a large number. It's a billion. And because of the antioxidant production, it's down to 1 million alterations per cell per day. And because of the repair mechanisms that we've had to evolve in order to stay alive, this comes down to another several orders of magnitude to 100 persistent alterations. And then we have mechanisms that remove the damaged cells, or the DNA damage. And so we end up with 1 mutation per cell per day. Now this is the comparative amount caused by radiation of a normal background of 1 millisievert or 1 milligray per year. So you can see we're looking at 1 million times less than what's happening naturally. Now, in comes radiation hormesis. For an acute dose or a continuous dose of radiation, we find that small amount of radiation stimulates the, this is the immune system here, from 100% at 0 dose of operating level, it goes up almost 80% higher at low dose rates, at low dose, single exposure, acute dose. And when you go to higher dose, it actually gets much lower. In fact, here you're wiping out the immune system. And this is in vitro and this is in vivo. So in living animals, again, you can wipe out the immune system with that kind of radiation. So this, the increase is not quite as large here. It's almost 50% increase due to a low single exposure. And if you look at the continuous exposure, you can see this type of a curve where you have an underexposed area. This is a beneficial area, biopositive. This is 0 equivalent point. This is normal background region. And here it's harmful. So organisms are stressed by any physical, chemical, biological, or radiation effect. The organisms adapt to the stress, and radiation actually modulates the organism's defenses. A low dose of radiation reduces cancer incidence because it stimulates prevention, stimulates repair, removal, and also removal of cancer cells by the immune system, while a high dose of radiation has the opposite effect. And so by looking at the sort of numbers you get with higher background, 10 times higher, 10 milligray per year, Myron Polyakov and Feinendegen attribute a number, let's say, of 7% here, 7% there, 7% increased stimulation for a total reduction for this higher background of 20% in mutation rate. Now, medical. This is Su-Shan Lu. He's a renowned radiobiologist in China, medical doctor, came to Canada, gave a lecture at our local hospital. And one of the slides he presented was an illustration of how the immune system goes after a cancer cell. This is a natural killer cell, and it finds a cancer cell, it grabs onto it, and it kills it. by injecting whatever chemicals are necessary to do it. And you see how it grabs on, doesn't let it go until it's finally gone. Now, Sakamoto used the method of treating patients with low-dose single exposures. This is half-body irradiation. He used a protocol of 15 rad twice a week, half-body. And this was done for 5 weeks, 150 rad, much, much higher than what you see at Fukushima. So this is the first patient that was treated in Canada, a colleague of mine. When I told him about beneficial effects of low doses and I told him about Sakamoto, he went into the hospital and he said he wanted treatment for hurdle cell cancer because there was no treatment for it. He already had the surgery and he was dealing with metastases and small tumors in his lungs. Hurdle cell is a disease of the thyroid gland, which is not receptive to iodine-131 treatment. So he keeps getting treatment every year to control his cancer. My wife had cancer. That's her there. She had surgery. It was removed. It was a stage 1, so there was no metastases found. But we gave her this treatment, 150 rad, 1500 milligray, twice a week for 5 weeks, 150 millisieverts, 10 times, as a prophylactic against cancer. So we're very confident that she's never going to get cancer for the rest of her life. Any metastases that may have been left from the tumor she had, we're very confident were gone. The physicians took blood tests every week. The radiation oncologist ordered them. And we monitored her blood variables. And just the last week, they checked her natural killer cell concentration in the blood. It was double what it was at the beginning. We have evidence that the low-dose radiation treatment doubled their NK cells and stimulated her immune system to fight cancers, including any cells that exist. This is cancer death rate in colon cancer in the US. It's 1986. It's from a book, Varmus and Weinberg, Biology of Cancer. You can see that with age, this is age 40, 60, 80, 100. The cancer mortality goes up quite dramatically with age. So that's the big factor. And if you put it on a log-log scale, you get a nice straight line. It's going up exponentially with age. And the reason for that is accumulation of mutations adding up. And the defense is getting old and tired. The immune system and other defenses are not working as hard as you get older, and so stimulation of the immune system and other defenses is beneficial. Now I'm wandering around a bit here, but I'm going to get back to Fukushima. I put in these extra slides because I have a bit more time here. This is the theory about radon, that increasing radon concentration increases lung cancer mortality. And Bernard Cohn did a study. He got many of his students students work for nothing. You get a paper, a degree. They checked 1,600 counties in the US. They got thousands and thousands of readings of radon. Now this is what do they call those studies? Forgot the word. Ecological study, that's it. In fact, I wrote it here, I think. Yeah, there. They didn't know the radon dose that each individual had for their entire life, but all he was interested to do was to test the theory. And the theory that's being used by the EPA and all the epidemiologists who are studying radon and lung cancer mortality is that it's a linear model. The more radon in your home, the higher the cancer rate. So Bernard Cohn said, I'm going to test the theory. So he measured radon in many, many homes in the US, and he correlated it with the lung cancer mortality in the county. And he found a contradiction. So normally, when you see this sort of evidence, you would reject the theory. However, authorities still accept it. So if you take the recommendation and reduce the radon level in your home by ventilation, you actually would increase your lung cancer mortality. So it's not really a good move to do that. I've also seen housing developments, one in Jerusalem, where after building a beautiful complex, it remains totally vacant because someone discovered there's radon in the land where the building was on. So there's a lot of fear about radon causing lung cancer mortality. Well, I could talk more about that, but I've got to go on. We have radium dial painters. They've been tracking, well, there's 4,133 have been identified in the US. It's a room full of some of them. They all had a jar of radium salt or phosphor on their desks, and they were pointing the brush and painting dials using their lips. And so they ingested radium, which is bone-seeking, and so it's possible to measure how much radium each one of these. So this is not an ecological study. These were actually, they knew how much radium each of these women had. Now, they didn't follow every one of these for their life, but they followed quite a few of them. And what they found was there was zero, pretty much zero, bone cancer incidence, right up to a dose 1,000 centigrade, which is quite high, especially with radon. As being an alpha emitter, people would attribute greater DNA damage, cell damage from an alpha particle. And so here you see a nice clean threshold, certainly not a straight line. And this was done by Rob Lee Evans, MIT renowned professor, published in Health Physics Journal, and people ignore it. But it's not a linear model. Radium, that's another, again, an alpha emitter. Apparently there used to be a problem with adenoids interfering with inner ear pressure. So these are Navy pilots, and these were children that had infected adenoids due to, well, children have a lot of tonsillitis infections until their immune systems get educated. But back then they were giving these children and these pilots treatment. They were putting radium probes in their nose right up beside the adenoids. And this is Center for Disease Control. Estimate 2.6 million in the US receive this treatment. 45 to 61 is the standard medical practice to shrink adenoids. It's quite high doses they received, very close to their brain, their thyroids, and no evidence of increased, no publication, no significant increase in brain tumors or thyroid cancer. They say children are very vulnerable to radiation. Well, you can call this an anecdote, but this child had a tumor in his eye, retinoblastoma, and he was treated by Henry Kaplan, a very famous scientist in 1957, lived his full life. And I'm sure I don't know the exact date of his death, but he had his sight restored. And so children, and there's a lot of studies. I have more references. I just don't have time to present them here. People keep saying that children are very vulnerable. We have to protect them. And that ain't so. Children have very strong defenses, in fact, stronger than adults. because they're dealing with the rapid growth of cells. Now, someone was curious about radiation levels, and someone was asking me about whether people getting whole body scans and x-rays in the airport was dangerous. And this is the bottom of the range. This is where we have all our regulations that protect us. This is where the medical diagnostics are. These are the doses for different diagnostics. This is the low dose program where beneficial effects are observed. This is where people study cancer epidemiology. This is acute radiation syndrome like the Chernobyl firefighters. And this is the doses used for treating tumors. So you can see there's a lot of, these are all factors of 10. And why they're regulating here when we see beneficial effects here, 2 orders of magnitude higher, is beyond me. Well, it's a good business, I guess, radiation protection. So this is the linear no threshold assumption. They fit a line to the Hiroshima and Nagasaki cancer mortality in the high dose range. They extend it to 0. If you put it on a graph which shows a log scale, this is in gray, this is in rad. And if you take a line and you plot it down to 0, you get a curve like this for a straight line on a log scale. And this is the normal incidence of fatal cancer due to spontaneous DNA damage. This is what is attributed to be the excess cancer risk due to radiation, the linear no threshold assumption. And they're protecting us against this risk, which goes all the way down here in the low dose range, 1 millisievert here. So they're protecting us against that gap between this straight line and the normal incidence. Meanwhile, we have a lot of data showing beneficial health effects in this low dose range. So this is the reality, and this is the protection concern. Hermann Muller, fruit flies. He was saying as a linear model that this is the repeated by Japanese scientists a few years ago. This is the mutation frequency at no dose. In other words, natural background radiation. And this is the Japanese measuring it more accurately. And here you can see it's actually a lower mutation rate at low dose range. And the statistics here are quite good. So Hermann Muller was measuring in this high range. And that's the basis of his linear model. Now, Edward Calabrese looked into all the records back at the time of Hermann Muller. And 1946, before he gave his Nobel Prize speech saying that there's no safe level of radiation exposure, he had evidence from studies at that time which showed that the linear assumption model was not valid. And he covered it up. And so Ed Calabrese has published 3 papers in the last couple of years exposing us. So going back to Fukushima, these are the radiation exposures of there's that many plant workers from March until December of last year. These are the suicide workers who were getting these huge doses. This level, 680, is the tolerance level that we're using for radiologists who are getting a health benefit. They 21% lower than their peers, class 1, in cancer mortality. So these are the suicide workers who are getting radiation exposure over that year, well, March till December, which is comparable to within the range of the radiologists' regulations back in the 1920s till the 50s. So it wasn't that bad, actually. Really, the workers were within the regulations of the radiologists. So what's the appropriate radiation level? This is the topic of my paper. So taking this Don Lucky's curve, and this is our ambient level. This is one is the deficient level. We're radiation deficient here. This is the hormetic region. This is the optimum radiation exposure. Here they're trying to keep radiation exposure within 1 millisievert below background. I mean above background, not higher than that. So this is what they're protecting us, as low as reasonably achievable. Here you see we can go to up to 1,000 millisieverts per year. And this is a better method, as high as reasonably safe. Because here we have another factor of 10 margin before it starts to get harmful. So really, for evacuations, this is the appropriate level for an evacuation, because when you take into account that evacuation causes a lot of stress, a lot of suffering for all the individuals, it affects the economy as well, agriculture, but also they shut down all the nuclear plants and started importing oil. So and not only that, they're trying to scrape the soil around Fukushima down to this level, 1 millisievert above background, which is really ridiculous when you consider no one evacuated Finland. So this is radiation protection activity, as you can see, which is not very pleasant. So my conclusions are that nuclear energy and also medical applications are blocked by anti-nuclear activists communicating myths about radiation and cancer. The radiation myth is not being debunked by anyone. There should have been outrage from professionals about what's going on, but no one's doing anything about it. I'm a lone voice. There's a few others, but not many. Nuclear regulations are overprotective, very costly in dollars and schedules for nuclear projects. The Chernobyl victims did not suffer from cancer. They suffered from vegetative vascular dystonia. So you medical people must know what that is. Jaworowski calls it a psychosis of fear. The other conclusions, spontaneous DNA damage is 6 million times higher than from radiation-induced damage. And this is Myron Polikov's conclusions. Based on human data, a single exposure of 1 millisieverts is safe. And my wife got 10 of those. Continuous exposure of that much per year is also safe. Both dose exposures are also beneficial. Radioiodine is not a significant cause of cancer, and that's a big issue with nuclear power plants. Low-dose radiation stimulates defenses. Total body low-dose therapy can be used to prevent cancer, eliminate metastases. Fukushima radiation was an insignificant cancer risk. Psychosis of fear causing enormous suffering. Residents need to know the true radiation effects on health, and in Fukushima they should be urged to return home. And the worker doses in Fukushima were below the 1931 tolerance limit. So those are conclusions, these are recommendations. Society should organize events and discuss this. Regulatory bodies should examine the data, stop calculating nuclear safety cancer risks, stop regulating harmless radiation sources, develop a public communication program, and raise the radiation level for evacuation from 20 to 1,000 millisieverts per year. And you probably know this fellow, Rahm Emanuel, used to be the chief of staff of Obama. He's now the mayor of Chicago. We should never waste a serious crisis. It's an opportunity. Fukushima crisis is the opportunity to change the ICRP protection concept from LNT back to what we had in the 1930s. So, these are the 3 points I try to keep communicating. Enormous rate of spontaneous damage is occurring naturally, and that required the evolution of powerful defenses. The radiation caused by X-rays is millions of times less. And low-level radiation stimulates the defenses and produces beneficial effects. So, and high radiation, of course, has the opposite effect. So that's my talk. And got a few minutes for questions. Thank you.
Dr. Cuttler,
Yes.
if the people who were evacuated had remained in that red area, would any of them have received any more than that worker at the highest level, which was still just 700 millisieverts, the level that Dr. Polyakov had recommended not be exceeded?
Well, the workers in the plant got much more than what people would have got outside.
There's no one then in the whole evacuation area that would have received that much?
Well, there were a few hot spots. People did look, and there were bits of radioactivity that did get out. The people in the plant were monitoring where they were going, and so I'm sure they did not get that high exposure. Well, we know what they got because they measured it. They had dosimeters. The people outside were not wearing dosimeters, but people were doing airplane scans, and they knew where hot spots were. And I'm sure they could have put a little fence around any hot spots if there was a large release coming out of cesium on the ground there.
And that there'd been a supply of these little radiation detection things that we carry, would the population have felt safe?
No, I don't think it helps to be carrying all these dosimeters. You basically scan and measure where they are, and then you put a fence around it, and you let people live everywhere else. And they would not have been, the thing is, people, especially in Japan, have been taught their entire lives about the scare that any dose of radiation is harmful. So it's very hard to suddenly change people's attitudes. So people still would have been afraid unless we introduce an education program, which will take many years to teach people. Otherwise, people will always be afraid of radiation when it's released from a nuclear plant.
Thanks. I'm John Utley with the American Conservative. Our magazine is on the table in back. And I wrote about this. I've written about civil defense over the years.
Yes.
And after Doctors for Disaster Preparedness newsletter with Dr. Orient pointed out about giving Geiger counters in Tucson, they had them only up to 15 millirem. And I wrote this up, and after that, Homeland Security on their website, right after 9/11, had said, get out of town if there's any radiation, if I'm remembering right. And then they changed it, but they didn't put any number there. So I've been trying to find out forever since then. I own an apartment house in D.C. a mile from the White House. If there's a dirty bomb put there somewhere and it goes off, under the current regulations, wouldn't they have to evacuate the whole of Washington? Because they're using the 15 millirem, I think, and I don't know the difference. I'm not a scientist, millirem and a millisievert, which please tell me. And you also, at Yucca Mountain, I read that the limits there is designed for the civilian workers at 15 millirem as well. So my question is, if we have a building in Washington, what should the fire department in Washington have to measure to tell them to evacuate the whole city or evacuate a block, 10 blocks from the White House, the literal numbers? And then when you say millisievert...
Wait, one question at a time. I can't remember.
Well, it's combined. It's combined with that.
Let me answer that one.
It's combined with that. You say millisieverts per year as opposed to one-time exposure. Go ahead.
There are emergency measures people in every city, and they should have detectors. People should stay indoors, and then they should measure how much is out there. It generally will not be harmful, but if it is harmful, then people in harmful areas should be evacuated until it's cleaned a bit. But we shouldn't wholesale evacuate everyone out. because, well, they did the same thing in Chernobyl. People living in the homes in the city, Pripyat nearby, they waited a few hours, maybe a day, and they measured, and they decided to bust them out, and it was done in an orderly manner, and these evacuees did not receive a high exposure. So I wouldn't generate a panic, although the first thing you have to do is educate people. Otherwise, you're going to get a panic. People are just going to jump in their cars, they're going to charge out, and if you thought morning rush hour was bad,
Yeah.
you know, it's not a smart thing to be sitting in a car for a whole day trying to get out of the city.
Well, so what measurement should the fire department have in Washington?
Well, they should have Geiger counters, of course. I'm sure the people will fly airplanes over the area. They'll see where the contamination is and how high it is, and they'll probably tell people it's not a hazard and not to worry about it.
Up to 1,000? You said that's over a year's time.
Well,
But I mean, it
the
dissipates.
thing you've got to be
So,
worrying about is the acute dose at this point, and it's probably not going to be very high.
so
I mean, if anyone's going to explode a dirty bomb, he's got to carry it. And how much lead is he going to put around it? And then if he spreads it out, it's not going to be that bad.
when I write this,
Well, if they use the proper model, I'm sure they could come up with sensible recommendations. I could sit down if you want me to help them, but I can't answer this off the
you
cuff.
can't say when I explain this in Washington what they
Well,
should have.
call
It's
me
not
and I'll
15.
come and I'll explain it.
Okay.
I can't do it here. Thank you.